The purpose of this video is to explain the beta distribution. And we're going to use the beta distribution. We're going to see that later on this week. When we're dealing with an experiment that has a binary dependent variable. So in other words, we've got either a success, which we'll identify as y is equal to 1, or failure, which we'll identify as y is equal to 0. And we're going to have a parameter theta, which is the long-run probability of a whole bunch of 1s and 0s. We can think of theta as being the expected value of the random variable y, when the random variable y can either be lowercase y equals 1 or lowercase y is equal to 0. So that's just an indication of why we're going to be interested in the beta distribution. And we're going to be interested in situations in which we're interested in having a prior distribution for the parameter theta of either a Bernoulli or a binomial distribution. So before digging into the details of a beta distribution, I want to do a warm-up thinking about the normal distribution. So here's the equation for the probability distribution of a normally distributed variable. What we have here, P at y, is the probability density of y given some specified parameters, mu, the mean, sigma, the standard deviation. So the way this would work is that we would need to specify the values of sigma and mu, and once having done that, we can simply enter y into the equation, and what comes out of the other end is the probability density y given our specified values of mu and sigma. And so, for example, if we'd specified mu was equal to 100 and sigma was equal to 15, and we considered all possible values of random variable y, then we'd see a mean at 100 and a standard deviation of 15. Now, the good news is that we don't actually have to deal with this ugly formula. Rather, all we need to do is specify that we've got a normal distribution with mean 100 and standard deviation 15. And if you ask R nicely, it will produce a plot like this. And in week 1 on eClass, you've got a PDF called Probability Distribution Plots that has some code that would allow you to specify mu and sigma and get a nice plot like that. So that's kind of a warm-up. Now let's move on to the beta distribution. So again, this is the formula for the probability density. As I mentioned, we're interested in some parameter theta, and this parameter theta is going to have as its distribution. It's going to have as its distribution a beta distribution. And it's going to have these two parameters, A and B. So, again, very similar to the normal distribution, how this is going to work is we've got this equation here, and we need to specify our particular values of B and A. And having done that, all we need to do is plop in a particular value of theta, and what comes out the other end will be the probability density of theta. A few things to note about this beta distribution is this stuff here, which is essentially telling you that the parameter theta can only go between 0 and 1, and that makes sense, because essentially what we're ultimately going to see is that this parameter theta is just the, as we indicated up here, it's just the probability, it's the value, I should say it's the parameter in a binomial or a Bernoulli distribution So that's what theta is ultimately going to be. But what we're saying here is that this value theta itself can have a probability distribution parameterized by A and B. Some features of the beta distribution are that the expected value of theta, in other words, we can represent that as the mean of theta, is going to be equal to A over A plus B, and the mode of theta that we're going to represent as omega is going to be calculated as A minus 1 over A plus B minus 2. And so if we were to specify, for example, A is equal to 4.6 and B is equal to 15.4, if we asked R nicely, or if you go into eClass and there's a program there called Beta Prior Generator, you could use that program, specify A and B, and you get a plot that looks like this. Now, Krushky has an alternative parameterization. And instead of initially proposing values of A and B, he is initially thinking about proposing values of the mode, which is omega, and something he refers to as concentration, which we represent as a K, and that's kappa. Well, it's pretty obvious what the mode is. I mean, that'd be the modal value right there. But what is this concentration business? Well, here we've got a plot that's hopefully going to demonstrate what that means is. So in each one of these cases, the mode is always the same, 0.75. But what we've got is increasing values of kappa. In other words, increasing values of concentration. And you can see as we go from kappa equals 5 to kappa equals 20 to kappa equals 50, the mode remains at 0.75, but the probabilities become more and more concentrated around that mode. And there's one way to think about this, and it's only an approximate way to think about it. It's not an absolutely definite way to think about it, is if you've got a kappa equal to 5, and a mode is equal to 0.75. Your best estimate of the mode is 0.75. How much confidence do you have in that estimate? Well, approximately, you can have as much confidence in that mode being 0.75 as you would have if you'd done 5 trials and use that information to get an estimate of 0.75. In contrast, if kappa equals 20, that's going to have about as much confidence in this mode of 0.75 as you would have had you conducted 20 trials, which you have n is equal to 20, and you got a mode of 0.75. And similarly, here you've got a high confidence that the mode is 0.75, as much confidence as you would have had you done a simple experiment with 50 trials and got an estimate of 0.75. So that's the way you can think about this value of concentration of K. But if we parameterize in our minds, according to omega and kappa, to get R to work, we're still going to need to specify the beta in the form of AB, which means that somehow we got to figure out, okay, how do we get from omega and K to A and B, which is what R demands. And these are just the equations, and they're developed in Krushky, but it really is a detail you don't need to worry too much about, that A is going to be equal to omega times kappa minus 2 plus 1, and that B is going to be equal to 1 minus omega kappa minus 2 plus 1. And so, for example, if we assumed that the mode was equal to 0.2 and that kappa, the concentration, was equal to 20, in other words, it had about as much confidence in this value of the mode being 0.2 as if we'd done 20 trials, then we could calculate A is equal to 4.6 and B is equal to 15.4. And so we could plop those into beta generator R, and that's what we get. A beta distribution with parameters A equals 4.6 and B is equal to 15.4.